chemistry. And that part was really interesting to me because you start out with oil, and here there's a lot of different oils, and I've brought some examples for you. Some of them are solid at room temperature, some of them are liquid at room temperature, and lye, which is like the lye you have except for only finer grains, and some things to make it smell good, essential oils. And you mix it all together, and if you're lucky and you do it right, it comes out in the end a bar of soap that is neither greasy like the oils are or caustic and burns you like the lye is. So, I mean, that's pretty amazing, right? You've started off with things that have properties that you wouldn't want to have anywhere near your skin. And you end up with something that you purposely put on your skin and makes your skin clean but not dry. Okay? Doesn't strip all your natural skin oils but still takes off the dirt. So the reason that can happen is you started off with something that dissolves in water, right? That you can make an aqueous solution of, and something that's not dissolved in water, that's hydrophobic, and you've mixed the two together, you come up with a molecule that on one side of it dissolves in oil, right? It's hydrophobic, and it'll dissolve in an oil solution or something that has oil on it, like your skin. And the other end of the molecule is aqueous and will go into a water solution. So you put the soap on your skin, and the oil part takes the oil, which is, got the dirt in it that's all over you, or maybe a lot, maybe a little, takes it into solution, into the water phase, and rinses it off you. So how's that happen, right? That's the saponification reaction that you guys have learned about, right? Where you take an oil, which is composed of fatty acid, backbone, and glycerol, break those two apart in the presence of a strong base, and then those combine, and you come up with the soap molecule. It's a reaction that has to take place in an aqueous environment, right? If you just mix the oil and the sodium hydroxide, it wouldn't work. If you left it out, since it attracts moisture from the air, if you left it out for a really long time in a humid environment, it would go a little, but it wouldn't go very much. So you're putting those together in an aqueous environment, and then you're starting the reaction. You can either let the reaction go on its own, which will be really slow, or you can give it a kickstart by putting some energy into it by stirring it and creating heat by friction. And then it's an exothermic reaction, and it will take over and kind of perpetuate itself. If you do it right, and you do it at the right temperature, and you cool it correctly, you come out with bar soap. If you don't, and say you cool it too fast, the reaction stops, the unreacted lye and oil separates, right, because it's not bonded together yet, and you come out with something that's like this except for has pockets of lye, which you don't want. And I've done it, okay? So one of the things that you guys get to do is read about the mistakes and then not make them. Of course, you probably will still make them. I knew about the temperature-dependent reaction, but what I didn't know at the time that happened is one of the ingredients I was using had less energy, and so the reaction was less endothermic, and I actually needed to provide heat for it so that the reaction would continue to go. And the reason I found out is I looked up, maybe in this book, but also on the internet, what happens? Why did this happen? And they said, well, it could cool too quickly, it could have not reached temperature, and I kind of went back in my notes and did what I'd done. So this is where all the really good note-taking and the whole way you do a lab notebook, you plan your experiment, you know what you're gonna do, and then you write down exactly what you did. So you can go back and go, aha, this is what happened. So at the beginning, when I was still doing the calculations by hand, now of course you don't have to do it by hand, there's a website where you can do it for you. I would take the oil that I was using, look up the saponification value, which is how much lye it would take to saponify each gram of that particular oil. And it's different because they have different carbon chain lengths and different, some of them have different double bonds, which I have listed here. So your guys are gonna come look at all this stuff. So I'd look at the oil I had, find out the saponification value, and then calculate it by hand. So I could tell how much lye I would need for each oil, which I would then use each of those values to calculate how much lye I needed at the end, given how much of each oil I was using and how big of a batch I wanted. Then I'd calculate how much water I needed as a carrier and start the whole process. So then when you look at, and actually this is an early one, and it says the date. You have nicer lab notebooks, I just did it on scraps of paper. The date, who I did it with, I did this one with my daughter Rachel when she was still in SAS. And the how many grams in each batch, what oils I was using, and what I did. So then my notes, like on this particular one, I would put these, I think it was cold or something. And so and the reaction goes faster if it's warm. So it said I turned the oven on to a certain temperature for 2 hours, then let it cool. How the sequence in which I added all of the oils, and then I would look at it periodically. And soap does a thing which you'll see called tracing. So first you have this melted oil, right? This solid, and it won't work unless you melt it. So you have melted oil or liquid oils, and a solution, an aqueous solution of lye, and they're thin, and you mix them together, and they just like a thin solution, and it'll start to thicken up and turn opaque, and that's called tracing. I don't know why it's called that. Do you know why it's called that?
Well, because like if you drips on it, you can kind of see.
Yeah, you can see it.
Drips. So
yeah, so
it's
it's
like
just
pudding.
kind of,
If you've ever made pudding, it's the same kind of pudding.
yeah, like a pudding thickening, right? And then as it's reacting, it'll do this thing called gelling, where it turns from opaque to a little bit translucent. It looks like gel, and that means the reaction's going properly. If the reaction doesn't go, you can end up with the ingredients not kind of going together, and it'll be really crumbly. Do you have examples from last year?
I do. I'm willing to show them a little bit, but.
What? Oh, they don't have to see.
I'll rip off the packaging.
Oh, okay, yeah. Take the names off. And you can also have, so that's if it's not warm enough, if the reaction doesn't complete. And the other thing that can happen is because it's, for the most part, a reaction that creates its own heat, if too much of that stays in. No. Oh, the crazy caustic one. Yeah, these aren't, this one's a little crumbly, but not bad. They actually did a pretty good job. You can have, if you have ingredients that can be overheated or burned, you can actually cause them to burn. Has anybody ever had like goat's milk soap, or that's kind of like a cool thing that people like, you know? So, but milk you can burn. Has anybody tried to heat milk up in a pan? And it scalds? It's horrible, right? It's got a lot of sugar in it, okay? And the sugar and the protein together, they can really burn. Well, you can put milk in soap to make a really nice milk soap that's really nice on your skin, but you can burn it which I once did, and I decided not to do that. So what I brought for you guys to look at is this book that shows actually the sponification reaction, has lots of information in it. The chart that I use when I'm deciding what kind of soap I want to make and what kind of oils I want to use, because different oils have different properties. Some oils lather really, really well. Some oils are really conditioning to your skin. So like if you have dry skin, it would be really nice. Some oils strip more skin oils than others. Say if you have kind of oily skin and you don't want something really conditioning. And some oils have things in them like that are called non-saponifiables. So plant material that comes out in the oil that doesn't actually participate in the saponification reaction, but contributes to the properties of the soap. Makes it feel good, makes it smell good, something like that. So that's my list. And you can see on, well, you can probably see, but I need my reading glasses. The different properties, here's the list of different oils. And this is something I got off the internet. And the different fatty acids across the top. And then on the right is this thing called the iodine number, which is a measure of how hard the soap will be when it's all done. And I should probably know exactly where that number is derived from, but I can't.
Iodine, they're gonna, anytime you have a double bond, so you should have read over the weekend about saturated and unsaturated. What is the difference between saturated and unsaturated fatty acids and fats?
You can't have water.
Not water.
Saturated have no double bonds.
Saturated have no double bonds. Unsaturated has a double bond. What's the double bond have to do with it? So what?
It takes out nitrogen.
It takes out two oxygens.
Okay, it takes out two hydrogens. What else?
It changes the shape of the.
Good. It changes the shape, and that makes it so they can't pack together. So things that have double bond in them tend to have what state at room temperature? Think about this. It's very logical. They can't pack together. What are they going to do?
Saturated
They're going to be liquids, right? So unsaturated have the double bond. Yeah, they're going to be liquids at room temperature. So the iodine test is a reaction. Iodine will react selectively with double bonds. And so what they're doing there is they're basically doing what's called a titration to determine the number of double bonds that are in that. And so the more double bonds are in there, in theory, I would think, we should check that, maybe I'm wrong on this, but more double bonds are in there, I would assume that the soap is going to be less hard because it's going to be more liquid.
Right, and you have to choose. If you have too many oils with a high iodine number, then your soap will be really soft in the end and will not last very long in your shower.
Does that make sense?
So actually I think I put this up here, it wasn't included on the chart. The length of the carbon chain and how many double bonds are in each, like linolenic acid is C18, it has 3 double bonds. Linoleic acid is C18, has 2 double bonds. The properties of them are really different though. And different oils have different compositions in terms of how much of each. So this will say, well, so one of my favorite ones, you guys are gonna love this, is hemp oil, which has, it's unusual, it has 57% of this linoleic acid, which is really nice. So it's conditioning, but it feels like it rinses off your skin really well. And then it has 12% oleic and 6% palmitic, which makes a very hard bar, and that's what you use that something that's high palmitic for, is because you want your bar to be hard enough to stay together. So you guys can look at all of these, and I actually, if I'm formulating a new kind of soap, I look at that and I think, okay, what properties do I want, and what oils am I going to pick to do that? Okay, having said that, the majority of any soap that you get, and partly due to cost, is it's made of coconut, palm, and olive. Okay? Coconut and palm mostly because They're really cheap. And actually this one, so this is, I'm glad you said that about the double bonds. Okay, this is palm oil, and it's hydrogenated. Okay, so that it's solid at room temperature, and it's really easy to measure.
So you guys, what does hydrogenated mean? That was on the picture.
Hydrogen atoms have been added to
So
make.
you add hydrogens, remove the double bonds, you remove that kink, so now they can pack better, right? So they tend to be more solid.
Right.
Oh my God, it all makes sense.
And guess what? It's a trans fat. So this is something like if somebody was going to deep fry in a restaurant, they would use this. Same stuff. It's food, right? Now, if you guys are going to go buy palm oil, you probably will get a different kind, and you get a kind that separates into two different parts at probably about 75 or 80 degrees. So in the summer in your garage, it would separate and you have to mix it in or you're not getting the same composition. So there's that, and you guys can come feel it. Castor oil, which is a really interesting oil because it makes really good lather. And then I just brought the avocado oil because, and you can open these and smell them and everything. Because this is one, it's a really expensive oil. It's actually made from avocados, which are a high oil fruit. But it makes a really nice soap that's really nice on your skin. And that's partly because there's those avocado things in it that are separate, called unsaponifilables, that are separate from the actual fatty acids. And then this is shea butter. You guys can actually come and look at all this stuff. Shea butter, which you probably have heard about because it's like all the rage in like lip balms and hand creams and stuff. And this comes actually, this stuff comes from Africa. Okay, then here's soap examples, which you can look at. And soap balls, which I make from the scraps. And what else? Okay, then over here, this is the lye. Do we want to open the lye, or is that? You kind of got to have goggles on.
Yeah, we don't need to open it. But you should, Sage and Zach, can you share with everybody what you found so far? Because they're doing lye for their toxicity study.
Lye kills everything, pretty much.
It's really, really
Like, what's the lowest concentration you've done?
0.125, and it killed
125 elephants?
moles. Malaria.
Malaria. Okay, that's actually that's still pretty concentrated. So they're going to go lower. But anyway, sorry.
Right, it's pretty caustic, huh?
Yeah.
What was the pH?
Sure.
What?
pH.
No,
I don't think we measured it.
So if you dilute it, I can't remember.
The pH, well, you tell me this. You should know this. Is it an acid or a base?
Base.
Fail. Okay. So I guess you wouldn't know that, but if the formula is NaOH, is it sodium hydroxide? What's the definition of acids? What do they increase? H. And what's the opposite of H kind of in chemistry? OH. So if something is NaOH, it's going to increase the concentration of OH, which is going to decrease the concentration of H. So it's a really strong base. So now you tell me this. A strong base would have pHs where? High, low, the middle? High. Okay? It would be good if you learn these basic facts at some point. At some point you really need to learn these basic facts. So high pH. So this is for everybody. A 1 molar solution of sodium hydroxide has a pH of 14, which is quite high. I mean, that's,
So as you dilute it, the pH doesn't actually go down.
it does.
Oh, it does?
Yeah. It doesn't go down super fast because it's a logarithmic scale.
That's what I was remembering. Okay, and we're like pH, what are we, 7.3?
Yeah, somewhere in there.
So what do you want what pH do you want your soap to be, actually, is a really important question. So soap actually turns out always to be a little bit basic, but you want to be really careful that it's not too basic. So when you do your calculations about how much lye and how much oil you want to use, you want to make sure that all of the lye is fully incorporated in the reaction and that you have, if you have excess anything, you have excess oil. So one of the things you'll see on these sheets is a table where you can choose how much percent of excess fat to have. And I usually choose around 6 or 7, depending upon kind of how I'm feeling. If you have, isn't that really scientific? It's kind of like cooking that way. If you have a very low amount of excess fat, then you have to be extremely careful that all your calculations are super correct, and what's more, the number you have for the saponification value of each oil is exactly right. And you don't, if you're not testing your oils, you don't know that. You're working off an average saponification value. So I just usually choose somewhere around 6 or 7. If you have too much excess fat, your soap will be oily and it will spoil. It will go rancid, just like oil goes rancid. So then you have to measure everything out, and you have to be really accurate. So I use this little scale in grams. You have to measure the temperature, and you have to be accurate, and you have to have something that can be put in a lye solution and not be eaten up. So a typical metal thermometer can't do it. You could use stainless steel.
Stainless steel is fine.
Okay, I just have this old-fashioned candy thermometer. You can use glass, because lye won't hurt glass. You can use plastic. You can use a coated metal or stainless steel. You can't use aluminum. You'll eat it up.
It's exciting. We definitely had that happen once last year.
Yeah, you have to use eye protection.
Not
Because
good.
if you get even the teeniest bit of lye in your eye, you're in huge trouble. I've seen your lye beads, and they're kind of big and they sort of stay put. The ones I use are really, like, they're the size of a head of a pin. And so one can fly and, like, get on your skin and it'll burn you. So that's really important. I like wear a lab coat, I wear gloves. Nobody's in the house, no pets are around. Because first you mix up the lye and it has to sit there and cool off because it's a highly exothermic reaction. And you have to have your oil and your lye at about 100 degrees each. If they're way different temperatures, they'll separate. If they're too cold, they'll take a really long time to turn into soap. If they're too hot, they'll separate. Then once it's traced, you pour it into these molds. There's 2 mold examples. There you learn about silicone injection molding.
No, but we'll talk about molding tomorrow.
Oh,
so.
okay. So these are just 2 different molds. One I don't have to line because it's got this non-stick silicone thing, and one that I do have to line with paper. Things I use as preservatives: vitamin E and rosemary extract, which doesn't smell like rosemary. And then all the different essential oils that I use to make it smell good. And that's really all they do, unless you're into aromatherapy.
So do you use any, you don't do any dyeing, do you?
I
or
don't do
colors?
any dyeing. Some of them are colorful because, so this has a bunch of different citrus essential oils, orange and stuff, and they have color, and this has cinnamon in it, and that has color.
So why don't you guys feel free to kind of
Yeah.
wander back there and take a look at what's back there. Please thank Stephanie very much for taking the time out of her day. As usual, it's 5 minutes short.
Oh, okay. Well, that's. Oh, cool.
Are we going to be using lye?
Yeah.
You can't make soap without